I was thinking, and I would like to talk to you, is more about this V shape that the ducks do in the water. I'm sure everyone has seen this also with the boats, and there are pretty similar effects when with supersonic objects or even with Cherenkov radiation, although the physics is a little bit different. So I'll talk a little bit about wave formation, water waves, and about the cone. Okay, so I will start. So we have this picture here. We'll have the U. It will be the velocity along the x direction, x-axis, and then the W along the z-axis. So you have to take in account the boundary conditions. So the vertical velocity will be 0 at the z0, and the pressure at the surface will be atmospheric pressure, and just the surface, it will be the variation of the height. It will be the velocity at the W there. So to solve this problem, we just have to have some equations. So we'll start with the momentum equations. Here we have the acceleration of a little portion of water, and this will be like gravity water waves. So it will just be, in this case, the gradient, the pressure gradient along the x-axis. And for the z direction, it will be the gradient pressure along the z direction and the gravity, of course. So we also have to take into account the mass conservation. So if we consider an infinitesimal square, the flow of matter inside the square and out the outside of the square, it must be 0. So it means that the divergence of this two-dimensional velocity, it must be 0. So these are the equations that I'm going to use to solve this problem. I must say that it's a simple approach. I consider that the fluid is incompressible. I would not consider neither viscosity nor turbulence, and no, I will neglect the surface tension effect. It's a simple approach, but it's enough to get an estimation and to see some physics on this problem. So we have the basic state where the water is just static. So I'll do some first order approximations. Like this is the little bit the increase. Imagine when the water is static, U and W are 0. So I'll just take I will increase a little bit the U and W, not all that for all the variables of the problem. So the momentum equations just simplify to these two equations. And combining these two equations with the continuity equation, I get this equation for P prime. So then it's just like straightforward calculation, and we got to this P prime. And from there, it's also quite easy to get the expression to W prime. The time dependence of this formula is given by Qt. So the aim is to get the expression for this Qt. If we use this boundary condition, we just get that Qt can be expressed as this, where the omega is it's just the square of g k hyperbolic tangent of kd. So I'll consider deep water. So the depth of the water just is much greater than the wavelength of the wave. So this will just be 1, and the omega will be just the square root of this. So we get the phase velocity to be the square root of these things. It's interesting because we have this dispersion relation that omega goes with the square root of k. So it means that different waves with different wavelengths will propagate with different velocities, and this will be important. And the group velocity is given not by the phase velocity, but 1/2. So now to this cone effect. At first, I thought that it would be because the duck was just going faster than the waves on the water, but it's not like that, because it doesn't matter what the velocity of the duck is. It will always have this V-like formation. And also, the angle doesn't depend on the velocity, so it's a different physics. What happens is that there's a constructive the duck, when it's in the water, it just creates a broad range of waves with different wavelengths. So there will be dispersion, and there will be constructive interference that will form the V. So I guess it's there. And now that I have this V, when I just saw it in the lake, I just thought of similar situations in other fields of physics. Not other fields, but other situations. But the physics is quite different. For example, with sound waves. We also, if we have a supersonic object, it also will lead to this cone effect. But here there is no relation with the constructive interference. It will be just that the object is propagating faster than the waves is creating. So it just creates this cone. It's like if the little man is here, if the plane, if you were to be with a speed below the sound speed, then the waves will arrive one by one, and it will be like that. When it is supersonic, the waves kind of arrive at the same time. That's because of that you hear like a loud bang, because there's increases quite a lot the pressure in this shock wave. So and the angle is quite trivial to get. It's just the cosinus of the angle is the velocity of the sound divided by the velocity of the object. So another similar situation is Cherenkov radiation. That's when a charged particle just passes through the electric medium with a speed greater than the phase velocity of light in that medium. So it's just like the sound wave. Imagine the light just goes here, but it's slower than the particle. Maybe it seems a little weird that the particle goes faster than the light, but it's possible when you have high energy particles. It's not that difficult, and it really happens. We have this equation for the cosinus of the angle, and we can see if the beta is near 1, I mean, if the particle is near the light speed, then this cosinus, if we are, for example, in air, n is also near 1, so this will mean that the cone is quite narrow. So a particle with high energy will give origin to this cone effect with a quite narrow cone. And this Cherenkov radiation is quite used, for example, in astrophysics experiments. For example, when you have cosmic rays that arrive at the atmosphere, and then they produce protons and electrons with high energies, and they actually have the speed greater than the light in the air. So we just have this Cherenkov radiation, and we use that to detect the origin and to try to understand some astrophysics concepts. It's used also in nuclear reactors and particle physics experiments. It's quite obvious. If you can detect the Cherenkov radiation and the angle, you get to know the velocity of the particle, then you have its energy. And if it's a high energy particle, it's quite a narrow cone, so you have also the direction of the particle. So it's obvious that it's quite used in detectors because you'll get to know a lot about the particle. For example, in the Super Kamiokande in Japan, it's like a big tank with tons and tons of water, and they use this effect. So the conclusion is like just that the speed of propagation for deep water waves is wavelength dependent, and this gives origin to the dispersion. This dispersion will give the origin to that V shape on the water that we'll see with the ducks and boats and that kind of thing. But we have this nice cone effect also with different physics and different situations when objects travel faster than the waves they create. So in fact, it's quite good that we can use this effect in some applications of experimental physics. It's still physics, so it's good. Okay.
Okay.
Thanks.
And let's ask Raul questions if you have some. Okay.
So why does the cone angle not depend on the speed for ducks?
Yeah, but because, for example, for sound waves, you see that's quite straightforward, that it depends. But the physics, that's nothing to do with the ducks. It's just constructive interference. Mm-hmm. I haven't done the calculations. I haven't had time to read all about this. But the physics is completely different. You have no reason to say that it should be dependent on the velocity, because it's just constructive interference. And you see, it's obvious. You see that with the ducks that go pretty slow compared with the boats. You see that the effect too. So the physics is different. It's interference between the different waves with different wavelengths.
Okay. So in principle, you could calculate that angle just based on.
See, yes, you can. I just didn't do that.
Yeah, just curious.
Mm-hmm, yeah.
Are there any other questions? If there are no questions, let's thank Raul again.
Okay, thank you.
So the next speaker is Robert.
Yes. Mm-hmm.